we can extend what we learned about heat generation in Cartesian coordinates to curved coordinates. Let's look at a copper wire, which is carrying electricity, and because it's carrying electricity, it's generating heat. This wire has dimensions of r sub 1, that's its outer radius. It is generating heat at a rate q dot gen, and has a thermal conductivity of k sub 1. The outer surface of the wire is at a temperature of T sub 1. The wire is surrounded by insulation on all sides. That insulation has a thermal conductivity of K sub 2. It has an outer radius of R sub 2 and a temperature at its outer surface of T sub 2. And the insulation is surrounded by air with a heat transfer coefficient H. We want to find the temperature distribution in both the wire and the insulation and sketch the temperature distribution. Our assumptions are that we're at steady state, we have radial symmetry, the system is invariant in Z, we have a constant thermal conductivity. So you can see here, we are no longer assuming, as we did much earlier in the course, that there is no heat generation, just like the last problem that we solved. So we're going to start by solving for the temperature distribution within the wire itself. And then, after that, we'll look at the temperature distribution in the insulation. So we're going to start by establishing a simplified governing equation. We have here the full heat diffusion equation in cylindrical coordinates. Since we have radial symmetry, we can eliminate any sort of angular dependence. The system is invariant in Z, which gets rid of this term, and we're at steady state. This leads to a much simpler governing equation. We can integrate it, and we end up with T of R equals minus Q dot gen R squared over 4 K sub 1 plus C sub 1 times the natural log of R plus C sub 2. Remember that this is the solution for the temperature distribution in the wire, which means that it has to be well behaved at R equals 0, at the center of the wire. If it has to be well behaved at R equals 0, that means that C sub 1 must equal 0. We can also apply an additional boundary condition that the temperature at R sub 1 equals T sub 1. If we apply both of these boundary conditions, that C sub 1 equals 0 and T at R sub 1 equals T sub 1, we end up with this expression for the temperature in the wire. So we've solved the wire part of this problem, but we now want to solve for the temperature distribution in the insulation. So we need to establish the simplified governing equation in the insulation. We start with the full form of the cylindrical heat diffusion equation. We have radial symmetry, which gets rid of this term. We're invariant in Z. We're at steady state. And this time, in the insulation, we have no generation. This is a key difference between the wire and the insulation. So we end up then with this governing equation. Applying the boundary conditions at R sub 1 and R sub 2, we obtain this solution. And it is important to emphasize that in the wire, we have a parabolic temperature distribution, but in the insulation, we have one which is logarithmic. We can eliminate T sub 1 in this expression by setting the heat fluxes in the wire and the insulation equal at their boundary, and that in turn will allow us to get closer to the solution that we desire. So let's sketch out our solution now and see what it actually looks like. As we mentioned earlier, we have a parabolic distribution in the wire itself, which is shown here. In the insulation, we have a logarithmic temperature distribution, and then of course we have Newton's law of cooling in the air itself. We can sketch out an equivalent circuit for heat transfer from T sub 1 out to T infinity. For heat transfer from T sub 1 to T sub infinity, we are passing through two resistors, one defined by the insulation and another defined by the air. This can be instead casted as heat transfer through one bigger resistor, one which combines both the insulation and the air. In this case, this resistor has a temperature T sub 1 on one side and T sub infinity on the other. It has a resistivity of R double prime effective and a heat transfer coefficient of H sub effective. And we define here a reference surface 1. We can match the flux at reference surface 1 to the heat transfer that then occurs through the insulation and the air. Q sub 1 double prime, which is the flux at R1, equals minus K1 dt dr, evaluated at R equals R1. So this is taking the gradient of the temperature distribution in the wire itself. We set this equal to the heat transfer through the insulation and air combined as one big resistor. So we have H effective at reference surface 1 times the quantity of T1 minus T infinity. The heat that is generated in the wire must equal the heat current that passes through the boundary at both R equals 1 and R equals 2. The first term of this three-part equality is Q dot gen times V. This is saying that if we take the rate of heat generation, which is normalized per unit volume and per time, and if we multiply that by the volume of the wire, assuming that we know the length L of the wire, we can then determine how much heat is being generated per unit time. We can set this equal to 2 pi R sub 2L times H times T sub 2 minus T infinity, the center part of this equality. This is the heat transfer through the air defined at the boundary at which we have the temperature T sub 2. We can also set this equal to the heat transfer at the boundary R sub 1. In that case, we have 2 pi R sub 1 times L times K sub 2 times the temperature difference T sub 1 minus T sub 2 divided by R sub 1 times the natural log of R sub 2 over R sub 1. This is making use of the temperature profile that we derived earlier. For equivalent circuits, we can write out H effective at reference surface 1. The inverse of H effective at reference surface 1 is given by bringing together the resistances to heat transfer, both in the insulation and in the air. The first term here, R sub 1 times the natural log of R sub 2 over R sub 1 divided by K sub 2 is for the insulation. This is a familiar form that we've covered earlier. And for the air, we have something that is based on the heat transfer coefficient in the air, as well as this ratio of R sub 1 and R sub 2. H is intrinsically defined at R sub 2, so its reference surface is at R sub 2. However, H effective is defined at reference surface 1. So this ratio of R sub 1 and R sub 2 acts to take a heat transfer coefficient, which intrinsically has a reference surface of 2, and makes it into a reference surface at 1. The best way to see this is to actually work through the math without using equivalent circuits, and to see for yourself that you discover this ratio of R sub 1 over R sub 2 to correct the reference surface for the heat transfer coefficient H.